Institute of Science and Technology, Chennai. Satyabhama 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 Institute of Science and Technology, Chennai. Satyabama 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 Institute of Science and Technology, Chennai. Institute of Science and Technology, Chennai. Satyabhama Institute of Science and Technology, Chennai.
முருகேசன் சார் வந்திருக்கதா சொல்றாங்க.
Ma'am, by what name sir came?
That's what. Yes, just see.
Shiva is not there. One Shiva is there, but audio is not connected for that.
Manju ma'am, by what name sir has entered? Yeah, I'll check. It's not available now.
Sir, name எந்த நேம்ல சார் இருக்கீங்க? ஹலோ.
Okay. Because we have to make sir as host.
Sir is in the name of Siva.
Siva?
Sir is the
Yes.
Sir,
Murugesan sir. Siva, SIVA.
So audio is not there, for that connection. No audio.
No audio is available, ma'am, for Dr. Siva.
Yes. Anyway, I'll try to make him as
Host. Oh, yes, sir. Yes, sir. We can check sir slide also.
Please ask sir to unmute the sound.
Sir, kindly unmute, sir. Sivaprakasan sir, kindly unmute your audio. So we'll check whether the voice is audible. Sir's video is available.
But your audio is not.
Audio is not showing, sir. Any difficulty, sir? Shiva, sir? His sir is not able to speak.
We can't get your audio, sir.
Sir, can we do one thing?
Yes.
You please go out, then come in again, sir.
Sir has come again, I think. Shiva Prahasam now, sir has put
Sir,
that.
oh, another. Okay.
Now it is available, you can see.
Yes,
But sir has to unmute also.
Two devices, right?
Yeah.
Okay.
You change it to that one, sir. Shiva Prahasam is that name, yes. Yes.
Can
Yes.
I release Siva now? Can I
Yeah, I
remove
think.
co-host option for Siva?
Yes.
Maria, sir, no problem.
Let it be like that,
Yes, ma'am.
Yes.
First,
We'll first.
and then.
Okay. We'll first check for that first Shiva Prahasam, sir.
Hello?
Yes, sir.
You can hear
Good morning, sir. Yes, we can hear you.
Morning, sir.
Okay. We'll start.
Yes.
Yes, sir.
Yeah.
Try to share your screen, sir.
Yes, we'll check that, sir.
You can see my screen.
Started sharing. Okay, sir.
Yes,
Okay,
yes,
visible, sir. Exactly.
Yes, nice, sir.
Okay. Yeah.
So we'll start, Murugesan, sir, shall we?
Yes, ma'am. You can start.
Yes. So good morning to one and all. On behalf of the Department of Physics, Satyabama Institute of Science and Technology, we welcome you to this 8th day of the 2 weeks FTP on pursuit of excellence in research and advanced technology. We will begin with a prayer song sung by Master Vasudayan. Vasudayan, you ready?
All, today I am going to sing a song on Brahma Mukate, which is written for Lord Vishnu. Brahma Mukate, Para Brahma Mukate, Brahma Mukate, Para Brahma Mukate, Para Brahma Mukate, Tandanana hi Tandanana Pura, Tandanana Bala Tandanana Bala Tandanana Bala Tandanana, Brahma Mukate Para Brahma Mukate Para Brahma Mukate Para Brahma Mukate, Tandanana hi Tandanana Pura, Tandanana Bala Tandanana Bala Tandanana Bala Tandanana, కందువగు హీరాది కమలంతు లేవు, అంతరికి శ్రీహరే అంతరాత్మ, హరే అంతరాత్మ, ఇందులో జంతు కులమింతానొకటే, అంతరికి శ్రీహరే అంతరాత్మ, హరే అంతరాత్మ, తందనానా హి తందనానా ಬಲ ತಂದನಾನ నిండార రాజు నిండ్రంజు నిండ్రయొకటే అందనే బంటు నిద్ర నదియూరొకటే నిండార రాజు నిండ్రంజు నిండ్రయొకటే అందనే బంటు నిద్ర నదియూరొకటే బెండగిన బ్రాహ్మణుడు మెట్టు భూమి ఒకటే చండాలుడుండేడి సరి భూమి ఒకటే మెండయిన బ్రాహ్మణుడు మెట్టు భూమి ఒకటే చండాలుడుండేడి సరి భూమి ఒకటే సరభూమి ఒకటే తందనానాహి తందనానా పుర తందనానా బల తందనానా బల తందనానా బల తందనానా కుదుగియ ముక్కు మీద కాయు ఎన్నొకటే కుదమి సునగుము మీద బలయు ఎన్నొకటే కదుగుణలను పాప కర్ములను సరిగా జడయుజి వెంకటేశ్వరునామొకటే కడుగుణలను పాప కర్ములను సరిగా జడయుజి వెంకటేశ్వరునామొకటే శ్రీ వెంకటేశ్వరునామము వెంకటేశ్వరునామము శ్రీ వెంకటేశ్వరునామొకటే తందనానాహి తందనానా పుర తందనానా బల తందనానా బల తందనానా బల తందనానా బల తందనానా నమస్తే.
Thank you, Asayan. Satyabama is a prestigious institution which excels in the field of engineering, science, technology for more than 3 successful decades. It offers multidisciplinary academic programs in various fields of engineering, science, technology, law, dental science, pharmacy, nursing, management, arts and science, and allied health sciences. The institution has been ranked in the 40th position by NIRF, Government of India, among the universities in India for the year 2021 and ranked one among the top 50 universities for 6 consecutive years. Our founder chancellor, Colonel Dr. JPR, established Satyabama Engineering College in the year 1988 with the aim to provide opportunity to deserving students to pursue engineering education. He has dedicated the latter part of his life to the cause of education, and we are ever indebted to our founder chancellor, sir. We also thank our Chancellor Madam, Dr. Maria Zira Johnson, our President Sir, Dr. Marie Johnson, and Dr. T. Sasiprabha Madam, our Vice Chancellor, and our entire management team for providing opportunities to conduct such academic programs online. So let us just begin with a quote from Tirukkural, which says that, எய்தற் கரியது இயந்த கால் அந்நிலையே செய்தற் கரிய செயல். It tells the meaning is, don't hesitate to seize opportunities. You can achieve even the hardest task. So let us see some opportunity from our resource person for today. And I request Dr. M. Manjula Madam to introduce our resource speaker for today. Ma'am, please.
Thank you, ma'am. Yes, ma'am. So very good morning to all the participants. We are very happy to welcome you all for this 8th day, 8th session of FLP. It's our prodigious pleasure to welcome our speaker, Dr. D. Prakasam, scientist, Center for Automotive Energy Materials, ARCA, IITM Research Park, Chennai, for this session on thermal stability of tissues in thermoelectric materials and devices. He has achieved his Bachelor of Engineering from National Institute of Technology, Tiruchirappalli, in Metallurgical Engineering and Material Science. M.Tech from Indian Institute of Technology, Bombay, Maharashtra, in Metallurgical Engineering and Material Science. And PhD from Indian Institute of Science, Bangalore, Karnataka. He has served as Assistant Engineer at BEML KGF, Karnataka, 1996 to 1998. He has 4 projects and 2 patents to his credit. He has more than 35 reputed journals publications and 14 conference presentations. His research areas of interest include nanomaterial synthesis, characterization, consolidation, structure properties correlation, XPS, SPS processing, thermoelectric materials, and device fabrication. In his academic contribution, 2 students are doing their PhD under his guidance, and 8 MTech students and 15 BTech students completed their PhD under his guidance. In awards, he has been awarded first prize in Electron Microscopy Conference in the year 2011 held at Hyderabad for Best SEM Investigation. He is also life member of Indian Institute of Metals, India, life member of Powder Metallurgical Association of India, life member of International Thermoelectric Society. So it's our great pleasure to welcome our speaker, Dr. Sivaprakasan sir, for this session. Sir.
Thank you, ma'am. Sir, please.
Am I audible, madam?
Yes, sir.
Hello? Yeah,
Yes,
okay.
sir. It's very clear.
Thank you very much, Dr. Malia madam and Dr. Manjula madam for inviting for this program, and I am really very happy to share my whatever the research work what we are carrying out at CIM, ARC over the past few years. As Dr. Manjula madam said, last few years we are focusing our attention on developing thermoelectric materials and using that material, making a device, solid state device, which can produce power from various heat sources available in various engineering applications. So in this project, it is a well-funded project, so we could be able to build a device, a prototype device, and now we are looking for some industrial partner to transfer this technology and make it into a large mass scale production. So this presentation, it talks about one of the less talked subject matter in thermoelectric, that is the thermal stability of the thermoelectric material. In fact, as an engineer, when you try to manipulate material into device, so the thermal stability is one of the most important engineering aspect in this material and device. So this presentation mainly focused on that aspect of the material and device. Coming to the thermoelectric technology, you are all very well aware of it, that basically a thermoelectric is nothing but converting without intermediate another form of energy, converting directly thermal energy into electrical energy. So it's basically a solid state technique, like your photovoltaic cell, PV cells extensively used for producing powers, where the photon energy from sunlight is converted directly into electricity. Similar way, here the thermal energy, that is a phonon, which is converted into electricity. But one material which converts directly heat into electricity is pyroelectric material, where some material, if you put it in some temperature, it will convert it into electricity. But here in thermoelectric, you have to create a temperature difference across the material. You take a material, you have to create a temperature difference across the material. That temperature difference creates a potential difference. So in that way, it is different from pyroelectric material. And in the same material, if you are not creating a temperature difference, it will not produce any potential. So basically, the temperature difference is the one creates potential. So why this technology is important? Why it is gaining a lot of importance in the recent past, though it is known for more than 100 years? This is gaining importance because in second law of thermodynamics, if you see, the conversion efficiency has the limit, Carnot efficiency. That is, you cannot produce any thermal system cannot convert or cannot have an efficiency more than Carnot efficiency. So in fact, Carnot efficiency is a good efficiency. It's more than close to around 2/3 is a Carnot efficiency in most of the system. But practically, if you see, in most of the thermal system, the work done, that is the effectively useful work done, what it is available is not even 50%. It mostly it will be 1/3 of whatever the energy produced from the burning of fuel or whatever it may be. So effectively, compared to the heat lost to the environment, the work done is very low. So in most any system you can take it, IC engine or generator, whatever it may be. So more the heat produced from the fuel or whatever it may be, it all goes as a waste, and very limited one goes as a work done, useful work. So now, as there is a need to improve efficiency of all these thermal engines, because you must be aware of it, BS4, BS5, BS6, like that. They important for automobile to improve the efficiency, or important for any thermal system to improve the efficiency because of the global warming, all these things. Now it become improving efficiency is not the choice of matter, it's a compulsion. So to decrease the greenhouse emission, it is important that you have to meet the BS6 in automobile or BS5, like that. So how to do that one? How to improve the efficiency? In automobile, it is 33% to 40%, less than 40% is a conversion efficiency from it as a fuel to the work done. So how to improve it? A lot of technology people thinks, and most importantly, whatever we are adapting to convert this heat into useful power, the technology what we are adopting also be a clean energy technology. Again, you put some technology which produces another environmental impact. That's not the right thing. So it is important that we should look for a clean energy technology. In that way, the thermoelectric, one of the, since it's a solid state material, solid state energy conversion, it's a very green energy and clean energy conversion technology. It doesn't have any moving parts, so no noise, no additional waste, additional generation of heat or nothing of this kind. So this is what people looking into for various applications. And most importantly, this system, we can produce a small amount of power, milliwatt. There are applications where only milliwatt is required or even kilowatt is required. So very wide range of power output, we can get it from this technology. So it's high flexibility in terms of system and configuration. So again, the heat source, you can produce even heat power from your body heat also. There are flexible thermoelectric, which even good enough to produce some milliwatt of power from your body heat. So some power requirement of milliwatt also can engine, and you can do up to even 1000 degree also. Some oxide based thermoelectric material where 1000 degree also can be converted into electricity. And again, it must be very easy to integrate. It should not have a lot of moving, vibrating part. All seeing that thermoelectric has advantage. So all these things resulted into now it is a close to $800 million business globally. If you take in 2020 projection, it is close to 800 million. It is expected to be more than $1 billion in another 2-3 years. So this is a very rapidly growing technology, both in market as well as publication and patent. So currently some around 5-6 countries are making product and related applications. Even as a researcher, you must have seen that our latest scanning electron microscopy with energy dispersive spectroscopy is coming. Unlike the olden days where we pour liquid nitrogen to use the energy dispersive spectroscopy, now all these are using thermoelectric and Peltier cooling to control the temperature of the EDS. So these products, you can find it in a lot of application. Now these latest modern cars, the car seat coolings are done with this kind of product. So the market is increasing. So India, mostly in the research level, material research level is there, and we want to push this to industrial scale and industrial adaptation. So to some extent we were successful, and now we are finding some partners, and probably in a couple of years this will come in Indian market, manufactured in India itself, you can find it. So this is the thermoelectric technology. This technology basically revolves around 3 aspects. The Seebeck effect, as you people very well aware of it, is basically a temperature difference across the material, creating a potential difference. Then the allied technology, similar technology is the Peltier effect, which is basically giving a potential across a material. It creates a temperature difference across the material. So this peltier devices can act like a heat pump. It can take heat from one place and push it into other side. So in principle, this can be used as a refrigerator, and this is where now extensively used, and a huge market globally is creating a big market, and a lot of products comes out, particularly in biomaterial applications, all those things. And the third effect is a Thomson effect, and this is basically when a current flow through a material, and if the material already is having some temperature difference, so there will be some ejection or absorption of the heat. So in a way, this Thomson effect is something like a parasitic effect to Seebeck effect. So whatever the power produced, whatever the potential produced, if you allow to pass through a load, then the current will start flowing. And the current start flowing, the Thomson effect will either absorb, push the heat outside. So in a way, it acts as a negative effect to the Seebeck effect or some kind of parasitic effect. So whole thermoelectric concept, everything is works on basically these three F's. Coming to the material, thermoelectric material and property. Thermoelectric material is basically three properties very, very important. One is Seebeck coefficient, that is thermo power, that is for a particular temperature difference, what is the voltage it generates. And then once the voltage generates, so you have to connect to the external load, the current flow should be there. So when the current flow is required, means you should have a high electrical conductivity. It means high electrical conductivity, low resistance you should have. And then you have to create a delta T across the material. So the material should have low thermal conductivity also. If suppose the material is like a metal, high thermal conductivity, you cannot create a delta T itself. The temperature difference across the material you cannot create. So you cannot create thermo power, and you will not have any thermoelectric effect. So all these characteristics, which are in a way opposing to each other, has to be optimized to get a parameter called ZT, that is figure of merit, which consists of S square sigma by delta. That is, the S square sigma is called power factor divided by kappa, that is thermal conductivity. This factor should be a reasonable value. Reasonable value I'm talking about is ZT, something like as much maximum as possible it should have. And why I'm saying reasonable means for a particular temperature, this plot gives what is the maximum possible conversion efficiency. So for a particular material, if you consider ZT of very low value, you will end up with very low efficiency. So at least you should have ZT of 1.5 or a minimum 1 or 1.5 to get a reasonable efficiency. And now, though the lot of paper reports about ZT of 1.5, 2, even more than 2 also, those people are reporting value of ZT a particular temperature. That is, what is the maximum ZT achieved at a particular, at what temperature, that is what. But the maximum ZT at one temperature is not going to give the required conversion. What we need is the ZT should be, the ZT value should be flat actually, so that over a temperature range, the ZT is almost comparable, so that effectively it can give a maximum efficiency over certain temperature range, so that you can make a device, the device gives good conversion efficiency over a particular temperature range. Because any application, if you take it, the application cannot work, no application can work only one temperature or very narrow temperature. So heat available will be over a certain range. So the material what we are tuning, what we are trying to do, should have ZT over a certain temperature range. That's the most preferable. Coming to the various type of thermoelectric material, normally it is classified as the low, medium, and high. Anything less than 200 degrees Celsius, the one used mostly in biomedical applications and low temperature applications. this is low temperature, and bismuth telluride or some kind of polymer material as the most extensively used or explored for this application. Most of the peltier, everything comes in this also. The medium temperature application is the one the world is extensively exploring, because this is where the huge impact you can make in terms of energy production. But in this medium temperature range, mostly intermetallic compounds are the one extensively explored, and there is a lot of material showing exceptionally good ZT value. And as far as the product market where you have a power generation system is concerned, except one or two product is still made of bismuth telluride and some material, you will find very difficult to get any commercial product of reasonable price. So this is where the full work is required, that is converting all this high efficiency thermoelectric material into usable device. Then comes the high temperature greater than 600 degrees Celsius. This is mostly oxide is the one appears to be more suitable, and some intermetallic or some compound like silicon, germanium, all those stuff, it's showing some result, but still it gives a good power. It can, since the temperature is very high, delta T can create very high, it can produce more power, but in terms of efficiency still much lower than because the ZT so far reported is very low for most of the oxides, and even for silicon, germanium, this kind of materials also. Then depending upon the application, you can make a rigid thermoelectric or you can make a flexible thermoelectric. This is the one common used for biomedical applications and sensors, all those stuff. Coming to the medium temperature, this I am talking about in this title, the thermal stability. So what is the thermal stability issues? If it is a low temperature, like you are making a thermoelectric device for body heat conversion into some power, there is no need to bother too much about thermal stability, because we are talking of ambient or little above the ambient temperature, nothing more than that. But this, as the topic says, we are talking more of medium temperature. This is where the big opportunities are there. When it comes to the medium temperature, something between 200 to 600 degrees Celsius, then obviously the thermal stability is very important. Why? Because the thermoelectric material mostly are semiconductor material, a degenerated semiconductor with a very good electrical conductivity. It's almost like a metallic conductor. And then the semiconductor has to be efficiently connected to the metallic interconnect, because in thermoelectric material, thermoelectric device, you have P and N type material. This P and N type material has to be connected in series continuously. So this is a around 5 watt module which normally have 129 pairs of P and N type material. All this pair has to be same like photovoltaic. Photovoltaic, if you see each one, the photovoltaic panel will have one cell. The several cells are connected in series to get some voltage. Similar to that, here the P and N pair has to be connected electrically in series. How it is connected? It is connected with a very high electrical conductive pure metallic material. So you will have a semiconductor and metallic material electrical contact. This contact is expected to be stable up to medium temperature, that is 600 degree, 500 degree elevated temperature. It has to be stable. It has to be stable thermally, thermophysically, and thermochemically. Then only the full device will work for intended operating temperature and operational duration. So this is what it is challenging. So that is why we are talking of thermal stability. Imagine that some electronic, a kind of a low level of electronic, not like a microelectronics or super electronics, has to work at something which has to work at the temperature of 400-500 degrees Celsius. Of course, the full leg will not be exposed to 400-500 degrees Celsius. Only part of it. If you consider this is the hot side, maybe if this is the hot side, means at least to few millimeter from this joint, you will have elevated temperature. When you come to the cold side, you will have normal temperature. if not ambient, at least 50, 60, 70, less than 100 degrees Celsius. At least small part of this material joined to this electrode is continuously exposing to very temperature. So what it matters is at that condition, does this material have adequate thermophysical stability? It means it should not create any stress or cracking, or thermochemical stability. So in terms of diffusing of material from electrode into this semiconductor material, or counter diffusions, or any sublimation of the material, that is continuously exposed to several hours. So there could be some sublimation, or if it is a little oxygen or something is that undergoing some oxidation and degradation. It should be free of all these things to continuously work this without degrading its performance. So that's very, very important. So again, structurally, in the case of rigid thermoelectric material, all these things are normally put between two substrates, ceramic substrate, because the ceramic is electrically insulator and thermally conductive. That's why we are putting a ceramic substrate, and all these edges has to be reasonably sealed from open atmosphere. You cannot leave it in the open atmosphere and heat it to 500 degrees Celsius, because all will oxidize and crumble. So it has to be hermetically sealed. If it is less than 150 degrees Celsius, 200 degrees Celsius, to some extent it's okay. You can pack it with something and then seal it with the polymer. This is how it is sealed here. You can see it's a commercial module. It is sealed with the polymer. But if it is a 300, 400 Celsius, means automatically you have to put it in a hermetically sealed container filled with either inert gas or vacuum. Vacuum, if you create it, the vacuum will increase the sublimation. So there are a lot of other alternate technology we have invented. Coming to the thermoelectric material, as this is very critical for making a power generating or Peltier module, we need a P and N type material, and mostly it's a narrow band gap degenerated material taken from this group. One of the elements should be always with this semi-metal group, this one. Like most impressive performance you can see in tellurium based one, tellurium, selenium based one, and now like lead telluride and then antimony telluride. So like this. So one of the constituent is required mostly from here, and sometimes a transition metal with combination with the semi-metals also tried. So normally the carrier density is between 10 power 19 to 10 power 20 per centimeter cube. Electrical conductivity will be very moderate, and most importantly the thermal conductivity. So this is very critical. Preferably it should be less than 1 watts per meter Kelvin. So most of the material it shows in this range, or if it is little high, as this value goes up and up, the thermoelectric material leg height, whatever you are putting here, that height required to create a delta T will continuously increases. These are all some of the high performing thermoelectric material in P and N type. But now commercial modules, if you see, most of the modules are low temperature module is made up of bismuth telluride. And these modules mostly 150 to 200 degrees Celsius only used, because beyond certain temperature its property started decreasing. So this cannot be used for very high temperature. Then when it comes to the medium temperature, that is 200 to 600, a lot of materials, the lead telluride, and then sputrodite, and zinc antimony. In fact, we tried all these material. The most important, these all the material, it shows a very good performance. But the point here is, I'll explain that it is extremely poor material in terms of thermal stability. So that is why, in spite of it shows excellent properties, so far no commercial module made up of lead telluride or zinc antimonies are available in the market. So these are all some of the market commercially produced and reported thermoelectric module and the material pairs used. And of course, the bismuth telluride is very popular. It is, anybody can get it in online also. A lot of products are available. But other than that, some companies tried this sputrodite, cobalt antimonoid based material, and then lead telluride Half Chrysler, MGTSA. There are a lot of such products are there, but commercially getting. I approached many companies, but the cost is extraordinarily very high, $900, $300, and many these products they stopped because it's not commercially viable. So that's why they stopped. So they claim that it can be used. See here, bismuth telluride, 20 watts you can produce at this cost, whereas almost comparable power output, the cost is exorbitantly goes in other materials. So that's why it's commercially feasible, and many of this product they closed. It is not available. I tried to approach them to get this product, and now it is not available. Why this is exorbitantly cost? Because of the engineering what they adopt to make this material thermally stable. So that's why it is the engineering they adopted to make this module out of this material, to protect it from oxidation, to protect it from sublimation, to protect it from any degradation of the hot side contact. All these things makes this modules usable at 500, 400, 600 degree modules very costly. So coming to our work in ARC, so several material we investigated, and two material we combined, and we have come to making a module level. One is a lead telluride based material. One of this material we are using in our module. This is for a P-type material, and then magnesium silicon stannite. This is for N-type leg. So combining N-type, this one, and P-type of any one of the things, we have developed a processing technology to make thermoelectric module, and our module stably working up to 400 degrees Celsius. So when we make the module, it is important to characterize these material stability thoroughly, and now I will explain how, even though this material showing exceptional high ZT value, how it performs in terms of long duration thermal stability. So coming to the first material, LASTT10. So we prepare this one by a typical process of melting and then processing by a particulate material process. It shows the required phase with a highly homogeneous microstructure and homogeneous distribution of Seebeck coefficient in the prepared pellets. And we made by two methods. Both are melting route, rock and as well as induction melting. This is a very slow process, and this is a very rapid techniques. And what we got is, in both process, since it's a melting process, there is only the melting methods are different. We are getting almost same thermoelectric properties and densities. Everything is comparable. There is no significant change. So we are, and our properties is comparable with what it is reported for this similar kind of material. So, but what we observed is, in this LASTT material, probably less than half a dozen papers talks about thermoelectric property of this material. But they are showing only one curve, how maybe one, I don't know how many times they measured it. Very rarely we find a detailed experimental and characterization. But to our curiosity, we want to, since we are trying to make a device, it has to be done in a proper way. You can't just take one measurement and say something. So this result. So 10 times we measured, 10 times we cycled the material, heated to the up to 700 Kelvin, and see how the electrical conductivity and the thermal conductivity of this material is varying. But to our surprise, what we found is that first time when we do measurement, in fact, we have done both heating and cooling. Not only we measured only by heating, we measured both during heating and cooling. The first cycle when we heat and cool, there is a kind of difference between the properties what we are applying obtained in electrical conductivity between the first cycle and the remaining cycle. So after 10 times, from second cycle onwards, you can see that all these almost comparable. Seebeck also is comparable, but electrical conductivity is also comparable. But in but the first cycle alone, both electrical conductivity and thermal conductivity, there is a kind of difference between the heating and cooling. So it means something in the as prepared condition, melting and then doing processing and making a pellet. And then first time if you measure it, if you take this data only by heating, this cycle alone, you take it, you will get some data. But this is not an equilibrium microstructure or equilibrium chemistry of this material. So this whatever we got is a pseudo stable microstructure. So then we analyze this microstructure and the phase diagram very thoroughly. What we understand is somehow this material LAST10, this stoichiometer has the tendency to form some kind of secondary phases like this at the grain bone. So this is the basic microstructure we want, required phase. And then apart from the required phase, you ended with a secondary phase here. This secondary phase basically consists of tin, tellurium, and antimony. It's a tellurium rich SBS and P kind of phases, which is appearing. Then this phase, what is happening multiple times when you heat and cool or isothermally hold, somehow this phase disappears. You see here, this is as prepared sample. But after several times you do, particularly the grain boundary, now wherever these phases were there, everything become porosity. It's all, something is happening. We can't say it is whether vaporized or sublimated or whether it's melted and infiltrated into the matrix. Something metallurgically happened, but at the end of this 10 cycle or end of several cycles, the initial microstructure is not retaining. It is changing into this, and that is why we ended with a difference in thermal conductivity, because the thermal conductivity, this porosity will influence the thermal conductivity as well as the electrical conductivity. So even though this materials in literature, they show very impressive ZT, all these things, it is very, very difficult as it is. If you prepare it and claiming something is not the correct way to do. You have to anneal it for long duration until you get a stable microstructure and a stable chemistry. Then what is the performance it shows is the very critical. Then this is a bit of metallurgy, and then we thoroughly analyzed it. So when we thoroughly analyzed this one, we found that the secondary phase, whatever these phases here, these secondary phases can melt and form a low temperature melting alloy. This can even melt at 600 Kelvin itself, close to 600 Kelvin itself, it can melt. And that is what, and our TG, DSC, our thorough analysis we have done. So now if something had melted, there is a small amount of secondary phase, it melts at 600 degrees Celsius. Then in spite of if it shows a very high ZT at high temperature, certainly this material cannot be used for that high ZT application. The ZT where it shows the maximum, until that temperature we cannot use it. So that's a point here. So one time if you measure it, two times if you measure it, it will show the impressive data. But certainly we have to see in the long run, because these are all multi-component system, and these phases, whether in the long duration is stable, is the big question. Otherwise, one time, two times you measure it, if you get some good data, you can claim something. But in actual application, it will not work. So now, effectively, this material, last LASTT material, is suitable something around 3 and maybe it's suitable around 300, 350 degrees Celsius only. It can use. But you may ask, why can we avoid this one? Can we avoid this type of secondary phases forms? But if you see the phase diagram, it's not that easy. Very closely, if you understand the metallurgical aspect of this one, avoiding this requires extremely precise control of the processing, and that is in industrial practice it is impossible. So this is the problem. People report 1.5, 1.8, all the stuff. Here we have submitted into some metallurgical journal this research. But when it comes to the thermal stability, and that is also, that aspect also we have to see before claiming something that is excellent material, good material, something like that. This is another letter already, sodium doped one. So in fact, first we tried this one for our module. We realized that it's not going to work. So then we switched it to another lead telluride, which is also reasonably good performing material. But when we do this one, this material doesn't have such a secondary phase. It's not forming any such tellurium with secondary phase. So, and we have done for several cycles and consistently it gives the density. There is no variation in density. The microstructure resistivity is also, excuse me. The resistivity and Seebeck coefficient is very consistent. There is no variation. And density also variation. There is no porosity after measurement. So relatively, this material is much better than this one. So we use this material for making the electric module. And of course, mechanically also very stable. So this subsequently processed into this material we have used is the P-type material in our module. Then the other material, N-type material, what we have used is magnesium tungsten. Sorry, Mg2SiSn, Mg-6Si. This is N-type material. This material is also very, very promising thermoelectric material. Extensively it is investigated because this is the one material which is showing figure of merit ZP more than 1. At the same time, you can say that all the three materials are abundantly available. It's not like tellurium, selenium, which is are very costly. Here it's a magnesium, tin, and antimony. All the three materials are very low cost. So if we effectively if we make a good thermoelectric material out of this, the module cost you can bring down substantially. But the critical aspect here is a magnesium, because magnesium in metallurgy, if you see, it is one of the in metallurgy there is something called Illingham diagram. It gives the oxidation tendency of all materials. The magnesium is, if you see in periodic table, even its oxidation tendency is more than lithium. It's extremely difficult to prevent this from oxidation. It's highly, it has a very high oxidation tendency. And the processing, melting, all these things, we have to do it in extremely controlled inert gas atmosphere or a slag covered at the atmosphere to make the compound. Otherwise, as far as the material cost is concerned, it's very cheap. So if we make successfully impurity-free Mg2Si, it's a very good thermoelectric material. That's why we chose this as the N-type material in our module. So we successfully prepared. It shows excellent homogeneity. And see, this is the results of, in fact, 15 days, 15 continuous days at 450 degrees Celsius, we anneal, and then we have seen the Seebeck coefficient and then resistivity. So it shows a very consistent, it is not degrading or it is not undergoing any thermochemical changes to change all these values. The power factor also, it is comparable. So this also shows very good thermal stability. It is unlike this LASTT, it is not showing any degradation or pore formation or sublimation or oxidation in normal condition up to 450 degrees Celsius. So these two material is the one we investigated and selected for making the module. Now coming to the device. Now we have taken this lead telluride based material and the Mg2SiSn and we built a device out of it. As I told earlier, the device required metal thermoelectric leg contacts, that is metal to PBT LX contacts and metal to Mg2SiN contacts. And then we have to protect the legs from oxidation resistance. These are all the three conditions which determine the performance of the device. So this is a typical process commonly used to make thermoelectric leg for the device. Sometimes in some compound directly melted and then annealed. From here itself you can just slice it and make dicing and legs like this. Or in some material you have to go to some kind of ball milling consolidation and then slice. So anyway you can do it. But these legs as it is you cannot bond with electrode, so it has to be metallized by using some thermal spraying or electrode deposition. you have to metallize the surface, the semiconductor surface, you have to metallize it. And then the dicing you can do by using same the photovoltaic silicon wafer dicing techniques. You can use diamond wires or some other technique. You can slice it whatever the shape you want. And this microstructure here I am showing here is just to explain to you the hot side, how critical it is. In one of the commercially available module, which the supplier claims it can be used up to 300 degrees Celsius. Here, this is a hot side junction. Here you can see that. So this is a thermoelectric leg, P-type leg or N-type leg. Then it is connected with a metal, that is zinc. Zinc is used as an electrode. Since the zinc melting point is low, it can diffuse into bismuth telluride. So they put aluminum as one barrier layer, the nickel chromium as another barrier layer, and then in between the zinc and this thing. So this is how they interface the hot side junction to prevent diffusion of zinc or aluminum into this. Because if zinc or aluminum are diffusing, then automatically the concentration of this thermoelectric leg will change. If the concentration changes, then the conductivity, Seebeck coefficient, everything will change, and in many cases the device will start degrading over the period of time of operation. Here the nickel chromium is the main content. This is the one which prevents the diffusion, and it is keeping things stable. At the same time, it is good electrical conductivity with very low contact resistance it gives. So like this is for N-type material. This is how it is integrated in the commercial model. Cold side, it's no problem because the cold side is a low temperature. So you can just either with lead soldering is good enough to do it. And what is the characteristics important is the electrical interface. The hot side electrical interface, it should have a very, very low contact resistance, because the leg produces voltage. When you are connecting to the load, the current started flowing through this thermoelectric leg. So when the current started flowing, the contact resistance available here itself should be low. Otherwise, this itself will heat. Excuse me. So this is very, very critical. That is the specific contact resistance. Like this, the resistance to heat flow also should be low. And this is our contacting lead telluride, whatever we made it. Nickel as an electrode, we use it. Here you can see that we tried nickel, cobalt, and iron, all these things. Directly contacting resulted into highly unstable contacts. There is a diffusion, interdiffusion between these two during the operation. You can see that the specific contact resistance is very high, and the Seebeck coefficient of starting material is 74. So this increases to very high. It means the material started diffusing into lead telluride and poisoning the lead telluride. So the direct contact of any of these electrode material to lead telluride will not result into any good metal semiconductor joint, stable metal semiconductor joint. So to improve it, we tried a different tin telluride as a diffusion barrier or contacting material. And then finally, we ended with a configuration like this, which is the one which gives a very stable, thermally stable metal semiconductor joint. The contact involves cobalt as an electrode, with cobalt tin telluride as a first barrier and tin telluride as a second barrier, and then you ended with the actual material. So this is very stable. Here you can see that you may ask why so many layers. It is not only the diffusion, it is not only thermochemical stability, as I was talking about thermophysical stability. It means a gradual variation in the stress should be there. Otherwise, a crack will create between the layer. Interfaces will crack. So when we directly put tin telluride, it works, but this mechanical damage is occurring. So that is why we put a 50-50 this layer. Here you can see that after 7 days, as prepared and annealed. Absolutely same Seebeck coefficient. You can get it. Excuse me. So this is for Mg to SiSn, the N-type material. Here you can see that the direct contacting of copper electrode to the thermoelectric leg. Effectively, it's a disaster. You see, as prepared condition, this is the resistance and Seebeck coefficient. After 15 days of annealing, you ended with completely different parameters. So if you try to make a module directly bonding this thermoelectric material with the electrode, it's not going to work. It will not be thermochemically stable. So for this one, we tried a different material, and finally we frozen stainless SS304 as the barrier layer. So once we put this one, this is thermoelectric material. This is the electrode in between SS304 as the diffusion barrier layer. Here you can see in the as prepared condition, as bonded condition after 126. Even after 15 days also, the joint is stable. The resistance is comparable. The power factor also comparable. So this joint is now perfect. It works up to 450 degrees Celsius without undergoing any thermophysical or thermochemical. It shows a very high stability. So this joint will work in the device. So like this, we made it for lead telluride as well as G2SiSn, a stable hot side joint making techniques we made it. And this we tested for 15 days. It works very well. This figure shows how the specific contact resistance varies with or without diffusion barrier. Here you can very clearly see that in the presence of stainless steel, the specific contact resistance is almost same. Coming to the packaging, I was talking about, yes, now you have a stable hot side contact. Cold side is not a temperature, it's not going to be there any problem. But how to protect the leg? I was talking that if it is low temperature, 100, 150, 200, it's not a big issue. You can put your polymer and protect like this. But above 400 degrees Celsius, like the one what I'm talking about, my device. So you cannot put this kind of, no polymer can withstand up to 400 degrees Celsius. So what to do? So in that case, you have to do this kind of hermetic sealing. There is no other option. And inside, either you can put some inert gas or vacuum. But if you put vacuum, a sublimation problem is there in most of the material. And if you put inert gas, you will have thermal shunt. It means the gas is there, means there will be a convective heat loss, parasitic losses. So what we came up with is a kind of solution. Of course, this is already known, but not for this kind of devices. There is a material called aerogel, silica aerogel. This material is known for extremely low thermal conductivity. In fact, this thermal conductivity of this material is one order lower than most of the thermoelectric material. So what we have done is we are using in our module and filling all these gaps between P and N leg. The empty spaces in the device, we are filling it with this kind of silica aerogel, so that there will not be any heat transfer from hot side to cold side through aerogel. At the same time, there will not be any sublimation. The aerogel will prevent sublimation, oxidations, so that the leg will be protected. So this microstructure shows the aerogel covered Mg to SiSn. Even in after 400 degree Celsius heating in open atmosphere, it shows very, very just a few nanometer thick oxidation only. So the material stable. But if it is that the aerogel is not there, within a few minutes itself, all will become powder. So this is the techniques we use it for covering. And of course, this is the prior reported devices by different other labs, and nobody has used this combination of material like Mg2SiSN and lead telluride. So we successfully used it because we used this combination because it's a comparable thermophysical and thermochemical properties. Like you can see that thermal expansion coefficients almost matching in these two cases, almost like a same material. This is very, very important because both leg undergo same temperature. So it should uniformly expand so that there will not be any stress created and cracking. So these properties are matching. That is why we took the pair, and it is a figure of merit also almost comparable up to the proposed working temperature, hot side working temperature. And then we made appropriate contact and bonding techniques, and we could be able to achieve very, very low contact resistance by manipulating these interfaces, all these things. And finally, we made small lab scale testing devices, and we evaluated its performance. This is a 4-leg device, and this is a 16-leg device, which now we are making 64-leg device also we have successfully made. And effectively we have to optimize to get 129-leg devices. That's where our ultimate target. To once we made it, we'll give it to industry for starter manufacturing. So this device gives 0.52 watts per centimeter square power density at 341 Kelvin of temperature difference across the device, and it delivers a consistent open circuit voltage. And this is for 5 cycles we measured, and subsequently we measured in long duration also. It is performing very well, and we failed a pattern. This pattern is came for review. We successfully defended, so this will be granted shortly to us. To summarize, so this is the work I'm trying to. Yes. To summarize, in thermoelectric research, the focus is, if you see 80%, more than 80% of the literature, it talks only of ZT, and they are reporting very maximum ZT. But the point is that all ZT alone is not the matter when you want to translate it into some useful devices for some applications or something. So along with ZT, the most important thing is whether this material can, at that at the temperature at which it shows the ZT maximum, can this material, the long duration, will be stable, at least thermochemically. Thermophysically, you can manage it with alternate techniques. Engineering, you can do that. But thermochemically, will it be stable? Otherwise, what's the point in it? Because most of the materials are multi-component system, 3, 4, 5 element constituents, and it's kinetics of degradation. All this will be very slow, but it will be reasonable. So that is also one thing people have to evaluate before claiming something very big. Say that this can produce and change completely like that. Otherwise, that is the one which is very important from the making device point of view. So here we took a 2 material, lead telluride and Mg2SiSN, and we found sodium dope lead telluride is better than this last 10, even though the Z is very good. And by combining it successfully with some kind of packaging techniques and bonding techniques and the diffusion barrier, all these things, we were able to make a module, and now this module can operate for very long duration without any degradation up to 400 degrees Celsius reliably. So it is a time for the thermoelectric group, thermoelectric people working to go beyond just only concentrating on ZT and start exploring other aspects also. Otherwise, as I understand, the last 10-20 years, lot of high ZT materials, excellent claims has been made, but very rarely any of this material is translated into any device or some kind of sensors or something. The main reason is this is the one. So you have to holistically you have to see before claiming something in this material whether it is okay. Just any material you put it in organ inert atmosphere and measure it, it will go very good results. But you have to see practical condition whether it is feasible or not. So that's my observation in this. This is one small part of the whole project what we have done, particularly focusing on thermal stability aspect of this device. So this is our group in ARCHN. We have some people, and all these people got PhD now. And just thank you very much. That's it. I'm sorry, I'm
Because the
suffering from.
participants,
Yes.
Yeah.
Yes. Yes.
can you drink some water, sir, before you can
Yeah.
proceed? Some hot water.
Yes, dear participants, you have any queries on this talk? Okay, you can open your doubts now. This is a time to open for your questions regarding this talk. I go for the adoption. Yes, participants, you can unmute yourself now. You can ask your questions directly to sir. Sir, we have a question here in the chat box. Can you able to see that? In thermoelectrics complex structures will reduce the thermal conductivity, but in the case of SNTE, PBTE materials or simple cubic structure, they have shown good efficiency. What would be the reason, sir? Can you able to see that, sir? I'll send it. In thermoelectric complex structures will reduce the thermal conductivity, but in the case of SNTE, PBTE materials or simple cubic structure, they have shown good efficiency. What would be the reason, sir? They are asking what is the reason behind the good efficiency of.
Yeah, as I in the presentation initially I told. See, basically the efficiency is of a material is determined from figure of merit ZT, and the figure of merit ZT is determined by those three parameters. And that is a Seebeck coefficient, electrical conductivity, and thermal conductivity. So in this SNT, PBT, all these things you see, it's a very excellent material. It shows extremely good thermal power. That is Seebeck coefficient. So the Seebeck coefficient is basically determined by it is a band gap. Basically, it should be a narrow band gap material. At the same time, a kind of dopant what you are adding, and that resulted into what kind of charge carrier density you are fixing. So basically, you have to play with these factors: charge carrier density, that is the dopant determine the charge carrier density, and apart from that, that dopants also determine the band gap of the material. So in the tin telluride, lead telluride, these are all the structure. It is in a favorable condition that resulted into very good Seebeck coefficient even at low temperature. So once the ZT is the one which is related to converted into efficiency. So the structure, yes, it matters, but apart from that, the electronic structure of the material is the one which decides the efficiency.
Yes, any other questions? Participant, now you can able to unmute yourself to talk. Yes.
Reason, sir?
Yes, ma'am.
Here one question is there. What is the efficiency of P-type PBTE compound? Generally, they are asking what is the efficiency of P-type PBTE compound?
P-type PBTE compound, what we have used is ZT comes close to 1.2, 1.3 we are getting at somewhere around 400 degrees Celsius. So that if you translated into power conversion efficiency, close to 8 to 9% you will get, 8 to 10% you can get at that temperature. Maximum I'm talking about.
Sir, is it possible can we get the same, for example, N-type MG, SI, SNO, sir? Is it possible, can we get the P-type also in that material?
Madam?
Is it possible, can we get the P-type also in that material?
Yeah. See, the Mg to SiSn somehow it's a very good N-type material, but the same material by tuning the structure to get P-type was so far nobody is succeeded. So what people used to do is similar, exactly similar material instead of M1, it uses manganese silicate, M1Si based one as the P-type they use it. They combine this M-type, N-type of magnesium silicate along with the manganese silicate as the P-type material and make the device. But if you make any device, it is the lowest performing material is the one determining the power output. So if you take one material with ZT 1.5, another material with ZT1, so effectively the ZT1 material is the one determining the overall efficiency. So in that way, the manganese silicate is a very poor conversion efficiency. That is why the overall device conversion efficiency is very poor. So one reason why we gone to lead telluride instead of manganese silicate is this is the reason, because both have comparable ZT, so that both actually you must have seen people go with a completely different material with a completely different chemistry. So normally the same material with a different kind of dopant is the one people uses. So you put one dopant, you will end up with P, another dopant, you will end up with N. Even the scutellite everywhere. But why they are going is other parameter will automatically you can fix it, like a thermal coefficient of expansion and a lot of other parameters automatically it will get fixed. But if you go completely different material, you will have a problem. But in this case, it matches. That is why we have gone for it.
Actually, secondary phase, the formation of secondary phase, that is very difficult to observe in phase diagram, sir.
Yeah.
Any.
So see, that's what that occurred. Whatever be the material you are trying, it is good. You have to see at least a binary or ternary phase diagram, because the secondary phase formation, there is most of the something making homogeneous is binary itself is tough in many systems. But most of this material we are talking about is go to ternary, quaternary, pentanary like that. It is something like a mixing 5 into a homogeneous with one phase single. It is extremely tough. But unless otherwise, once you decide that I go for a four element, 5 element, you have to be very thorough about what are all the possible combination it can give unwanted phases. That you must be very well aware of. Yes, certainly you cannot mixing 4 or 5 element into a homogeneous single phase. You must have aware of this high entropy alloys, all those stuff. It's only certain combination of atomic sizes only you will end up with a single phase. Otherwise, the secondary phase will automatically form, because each element will have a different affinity towards the other element in the system. So you will always end up. So in this case, this LASTT, the antimony has more affinity towards tellurium. The tellurium has more affinity towards antimony rather than lead telluride, PBT. So that's why part of the tellurium from PBT came out and formed with the SB and SBT-TESN it forms. So this is the aspect. But what I'm saying is that with the cases which gives excellent thermal conductivity by phonon scattering, all the stuff you can get it. But you must aware of it whether these phases will be stable. So you put it into something and with respect to temperature and time continuously grows, degrade, sublimate, oxidize, then you will end up with a non-stable system. Any system, at least it should be if it is continuously in transient state, what you will get it out of. It's a problem.
But in theory, we are going the maximum temperature range 1000, like that 1200. In experiment, what is the maximum temperature range we can do, sir? So
That you have to as a the theory, people who do theory, they have to be little along with your theory, because along with your theory, the system what you are taking, you have to see the phase diagram, all those things also. It's very important, because I saw there are a lot of people projected properties for thermoelectric material beyond the melting point of the, I don't know what to say. See, you have to see that I saw in one paper in zinc atom, the melting point of the compound is something X, means simply they projected up to the whatever the temperature it is possible theoretically, but that's not the way to do, because beyond some point the structure changes, phase changes. So once the phase changes, obviously the electronic structure can be same, right? So once the electronic structure changes, then no more those parameters what you put it in the calculation is same. So you have to, along with your theoretical one, you will see the corresponding phase diagram also, phase change also. That's very important. Up to what temperature this phase can be stable.
Yes, sir. Any reason, sir? One more person.
Sir, one more question we have in our chat box, sir. Could you please elaborate the synthesis of magnesium silicon tin alloy, since magnesium is flammable in bulk form? Magnesium is flammable.
Yes. Magnesium is flammable. In fact, if you see people, the high-end products, high-end commercial cycles, there are titanium cycles are there, which is very lightweight. You can just, anybody can lift and put it, maybe 3 or 4 kg only. Like. And even aluminum alloy. See, the magnesium, titanium, aluminum, all these things become engineeringly relevant material, considering it's a very good strength and low density. So imagine your cycle is a very good cycle, good strength, same like your whatever you are using, but the weight is 1 kg or 2 kg. It's very comfortable. You can just fold it and wherever you want, you can take it. But why there is no magnesium cycle? Or because why there is, the problem is large scale. This question is very nice question. We are large scale manufacturing of magnesium alloys and casting, forging, rolling, all those things is very costly affair. But there are technology available. Even in India itself, it is available. The technology is mostly with the public funded institute like ARC, NFC. Commercial, I'm not sure, but defense sector, a lot of furnaces, lot of facilities are available. But it is a large scale manufacturing is possible. It is a slag they will use it. Yeah, there is a kind of slag is there, a sulfur based slag is there. So they put the magnesium and cover with a kind of salt, and that salt will make a impermeable slag over the molten metal of magnesium, and it will cover from the atmosphere, so that the atmospheric air cannot penetrate through the slag and react with magnesium. So that is how most of the reactive materials are made. For that matter, even melting of steel also, if the slag is not there, simply steel, if you melt it in open atmosphere, the steel, that also will oxidize. It will form no material except gold. You can melt it in open atmosphere without any slag or covering protection. So because everything has the tendency to take oxygen and oxidize. Yeah. And magnesium, yes, magnesium is highly reactive, but there is a slag cover will be there. Titanium is melted like that. Compared to titanium, this is more relatively easy. That is why we don't have titanium melting also in India. Only the defense lab they do, because the titanium you cannot put it in any container and melt it. That's why they do skull melting. The titanium will be melted in the titanium crucible itself. So part of that crucible is part of the molten metal of titanium is used for cooling it. So, whereas in the magnesium, it is a slag, a kind of slag with the atmospheric gas. There is a sulfur-based gas required to cover it. Yeah.
Thank you, sir.
Chennai one institute, they have the techniques. Yeah.
Thank you, sir. Thank you. Participants, any other questions?
Okay.
If no other questions, we can move on the next part of the session.
I request Dr. S. Murugesan to give the vote of thanks.
Thank you, ma'am. Thank you so much. So let us start a vote of thanks with the words of Bharadiyar. Without remembering Mundasa Kaviஞர் Bharadiyar, we cannot think about modern Tamil and Tamil Nadu. Everybody can feel proud of their motherland and mother tongue without disturbing others. I will try to go for some words of Bharadiyar now. ஆயுதம் செய்வோம், நல்ல காகிதம் செய்வோம், ஆலைகள் வைப்போம், கல்வி சாலைகள் வைப்போம், ஓய்தல் செய்யோம், தலை சாய்தல் செய்யோம், உண்மைகள் செய்வோம், பல வன்மைகள் செய்வோம். காவியம் செய்வோம், நல்ல காடு வளர்ப்போம், கலை வளர்ப்போம், கொல்லர் உலை வளர்ப்போம், ஓவியம் செய்வோம், நல்ல ஊசிகள் செய்வோம், உலக தொழில் அனைத்தும் உவந்து செய்வோம். Those are all the golden words of Bharadiyar. Bharadiyar, actually the meaning of those phrases are, Bharadiyar asking us to make weapons for defense. Weapons for defense only, not for threatening others, like some other countries do. A paper for education. Now we are in paperless electronic world. At that time in Bharadiyar's era, paper may be new and revolutionary. Again, asking us to make industry for development, school for intelligence. Bharati says no rest and laziness until reaching the heights, as Swami Vivekananda says. If you see Ayudham as weapon gives you a wrong meaning, say it as defense. It gives a right sound, and then we can have the proper connecting between defense and education. With our education, we have to protect our country through the society where we are living. Like this, Bharati connected contrast Tamil words in right sense. Also asking us to make literature and fine arts to reveal our culture to other countries. Forestation to avoid pollution. Today we have to make, we are in Make in India. But Bharadiyar talked about this before independence. You just think about his vision to solve all the problems what we have today after 100 years. On behalf of the management, Vice Chancellor, organizers, and our department, I thank all the participants for joining 8th day of 2 weeks international faculty development program on pursuit of excellence in research and advanced technology. It has been started at 20th and going to be ended on 30th of this month, 2020. I extend a really hearty vote of thanks to Dr. D. Sivaprakasam sir, Center for Automotive Energy Materials, Chennai, to spare his time from his busy schedule and given us very nice and informative talk on thermal stability of issues in thermoelectric materials and devices. Such clearly explained the low, medium, and high thermoelectric devices and its differences and advantages. Thermal stability of different combinations are also shown and suggested some important material for manufacturing. Okay, then for making device. Okay, at last we all waiting for making device only. That is comfortable for us, I think. Okay, so for our comfortabilities are suggested some important material from this talk. Thank you, sir. Thank you so much having the informative and excellent enthusiastic session for us. Thank you, sir. Thank you so much. Once again, I thank all the participants for making this event a successful event, because we are crossing 8th day, we are nearing closure. Then you all being here for making this event a success. Thank you all the participants. Once again, I thank our resource person for making this day a successful day. Thank you, sir.
Thank you, sir. Kindly all the participants, tomorrow timing, sir, 1:30 to 2:30. We have Dr. Sarandan sir, CSIR Institute. I think that will be another very interesting talk.
Thank you.
Yeah, thank you, sir, for that.
Yes, sir. Thank you so much.
All the participants join tomorrow session at 1:15 itself, isn't it, sir?
Okay.
Shall we wind up?
Yeah.
Okay.
Prakasam, thank you so much, sir.
Thank you.
Thank you so much.
Yes, sir. Thank you, sir. What about feedback, sir?
Yes, our feedback link is posted. Okay, 1 minute, sir.
Okay, just remind that, sir.
Okay, 1 minute.
Yes, fine.
It is already posted to some.
Okay. Participant, kindly fill up
the
the
feedback link is posted.
Yes.
Yes, you all take your own time, fill it up, then tell us, okay, we'll close. No need to worry about, okay, we'll close the meeting only after all filling up the feedback form. Yes, we have a lot of feedback forms in the chat box. Then I can choose your own. Keep in mind, I take your own time to fill up this form. Okay, try to fill it up without any mistake, without even single mistake.
I think most of the participants have filled. Still 60 are there.
Yes, ma'am. We'll wait one more minute.
Yeah, we will wait.
Ma'am, tomorrow timing?
1:30, ma.
1:30, ma'am. Thank you, participants. Thank you so much. Thank you for your great support.
Again, one guy asking feedback link.
No problem, sir. We will put it.
The link is there in the YouTube channel also. Suppose anybody want to go for this talk once again, I can go for the YouTube link. Already provided, for this 8th day talk. Then link, feedback
Thank you,
link
sir.
also
Thank you.
provided. Feedback link also provided in YouTube description box. You can go and submit your feedback. Can we
Yes, sir.
go for end of the session?
Yeah, we will end up the meet.
We hope you all filled up the feedback form. Thank you all the participants. Tomorrow exactly 1:30 p.m. again. Thank you all.
Join at 1:15 itself. 1:30 is the program. Yes. Thank you. Yes. Thank you, sir.
Thank you all the participants.